Hello and welcome to the second video for the IR spectroscopy experiment. So in this video, we're going to talk about activity 2 and beyond. So in activity 2, we're being asked to look up on the NIST webbook the harmonic first and second harmonic potentials for molecules in their ground state. This will be denoted as the X state in the NIST webbook. We'll talk about that in a moment. And then within the constant diatomic molecule section for a few molecules. And then we're asked to complete the calculations of the harmonic frequency in units of wave numbers, inverse seconds, and the force constant from this calculation. So we're going to start perhaps with O2, or you can begin with O2. One of the things that we can relate is that what we're trying to do here is use the vibrational energy that we can get in units of wave numbers by saying, okay, so our fundamental frequency will be the difference of energy from G of 1 minus the G of 0. So this is like the energy in V equals 1 minus the energy in V equals 0. So the fundamental frequency is just that difference of energy between these two different vibrational energy states. Well, for energy of a function of V, this is an equation from the previous page. It's harder for me to slide. So I'll just write down this equation, how it's not 1/2. It's omega E V plus 1/2. And then minus omega E xe V plus 1/2 squared, and then plus omega E ye V plus 1/2 cubed. Okay, so we have this equation here for G of V, the vibrational energy is a function of the vibrational quantum number V. Well, what you can do is plug in a 1 here, a 1 here, and a 1 here, and then work that out, and then minus plugging in a 0 in place of V. And take the difference, do some rearranging, and then try to solve for what the fundamental vibrational frequency will be in units of wave numbers. Now, once you have this value in wave numbers, it's relatively easy to, I hope it's relatively easy, just to use the conversion that we derived earlier from the equation C is equal to lambda nu, and then just account for wave numbers in inverse centimeters and your speed of light perhaps in centimeters per second to make the units work out. And so you can solve and relate that over to frequency in inverse seconds, and you can use that value with the equation that we were using on the previous page in activity 1 to solve for a force constant. Now let's take a look on the next slide on how we actually get into the NIST webbook. Okay, so in this chemistry webbook, all you got to do is search for, the way I would do this is just search for NIST chemistry webbook in a browser. So let me see if we can get this to work. Do a simple web search, and then here we go. We'll just click on the NIST chemistry webbook. I like to do formula search. We'll just do HCl. Let's actually do O2 because that was the first one that it was wanting us to do the calculations on. So we search for O2, and then what we're looking for is the constants of diatomic molecules section. Now you see here there's some various term symbols. Now they define their terms slightly differently than I do. They call the vibrational frequency omega E the first term. I call this the harmonic frequency, and I call this, what they call the second term, I call the first anharmonic frequency. Then the term they're calling the third term, I call the second term, but I call it the second anharmonic term. So just making sure we pick up on this notation. So I'm calling omega E the harmonic frequency, and then the next two terms are just the corrections. So they're the anharmonic corrections, the first and the second anharmonic corrections. But notice that these are going to be given in this table in inverse centimeters, and most of the values here are in inverse centimeters. We'll see a bond length will be given in units of angstrom. Some of these terms here, I guess from the BE down, we haven't defined yet, but we'll go through what those are later in some future videos. And so let's just scroll down on our chart here. Okay, why can I not scroll all of a sudden? Okay, now I can scroll down. Okay, now one of the things that this chart's doing is you may think that the first sort of data you would want would be at the top, when really it's at the bottom of the chart. And once I get to the bottom, I'll explain what these um, entries are. So here's our ground state or X state. Now for oxygen, you might remember oxygen has a triplet ground state. I don't know if we need to get into this here, but you might remember from the MO, molecular orbital theory, maybe as early as Gen Chem or maybe in PChem, that oxygen has two unpaired electrons in a pi star molecular orbital. And so those two unpaired electrons would give it a triplet ground state as opposed to most stable uncharged molecules have a singlet ground state or zero unpaired electrons. But nevertheless, the X state is our ground state of oxygen. We see the harmonic frequency, the first correction, the second correction for the omega E, XE, omega E, YE. And then you see some other data given here as well. The hyperlinked numbers are references. So some of these numbers are references. The subscripted number is the plus minus value in the last digit. So like when you see the _1 or _7, that's telling you that like for the omega EYE, that it's 0.0474 plus or minus 0007 wave numbers. So that last digit is telling you something about the uncertainty in the values, just give you a sense of what this table's telling you. You can hyperlink some of these references if you're interested. Like if we follow, I think I can just click this reference here. Okay, doesn't work with clicking it, but you can just go down and look for like that particular reference down here. Or maybe that's a note. Maybe note 69 is the note. The notes are in a weird notation. I wonder if this would look better on a web browser on a computer than something is screwing up, probably just on the iPad version here as I scroll through. But anyways, the higher states, the A state, the B state, the C state, these are what you call, these are different excited states of oxygen. And so these are the various electronic excited states of O2, and then you can see some of their data is known in terms of harmonic and anharmonic corrections to their vibrational frequency, and a lot of these values actually aren't even known. But so the values as you go up are higher excited states. So that's why our ground state on the bottom, and then our excited states above it in terms of the energy and higher. The TE is actually how much higher in energy the ground state is. So the term symbol or the TE is the energy that each excited state is above the ground state energy of just 0. Okay, but so for our case, the only state we're ever going to be interested in, we're not changing electronic state, is we're always in this experiment looking for that ground X state. And then we can use the data accordingly from it. And then here, one other thing you see is the bond length, unit angstrom, everything else here, units of wave number.